So we have that a charge is put into some electric field, and from that it feels some electric force. That electric force will cause that charge to move over some distance. By definition, that's work. So how do we go about understanding the work done by an electric field and hence the electric potential energy? Let's take a look at an example with gravity. So with gravity, which is much easier to understand, so I want to recall, again with gravity, we have, let's say that we are really close to the Earth's surface. We have the ground here. So this is our y equal to 0 here on the ground. And we have some object, which is some height above the ground. Let's call this mass m. And we know that it sits in a gravitational field. And we know that the gravitational field would point down everywhere. Okay, so that's our gravitational field. We know that when the mass is put in that gravitational field, that it will feel a gravitational force based on it. So we know that, for instance, it would pull it down. Call this Fg for force of gravity. And we know that the force of gravity is equal to mass times the gravitational field. This is also known as the weight of the object. So we have a force acting on a mass and it pulls it down through some distance. So let's say we go through some distance all the way until we get to the ground. Okay. Let's call this distance, delta y, or h. We can find the work done by this by recalling that work is the product of force and some distance. It's a little bit more than this. It's actually a dot product which relies on an angle, but for now, let's just say that this is force times the distance we move parallel to the force. So the force is down, then we move a distance in the direction or along the line of the force. So if we put that into there, we have that the work done by gravity, for instance, would be the force, which is m times g, times the distance moved, which we called delta y. Okay. So this ultimately is just potential energy, because potential energy is just the ability for work to be done on an object by a conservative force such as gravity. So we can use a very similar idea for electricity to understand how that works. So what we're going to do is we're going to have, let's say, this area or plate of negative charge. And let's say that we also have this area of positive charge, or another plate here. So this is positively charged. So there's a bunch of positive charges up here and a bunch of negative charges down there. We know that charges will emit electric fields. So what will happen is all the positive charges will try to emit an electric field in every direction away from it, and the negative charges will try to do the same thing towards it. What ultimately happens in the end is that we get this electric field that ends up being relatively uniform between these two regions of charge. So we'll consider that this is a uniform electric field, which means again that its magnitude and direction is constant everywhere. So no matter what point we pick in this region of space, same magnitude or strength and same direction. So in this case, we're calling it down. So we have an electric field that goes from the positive charges toward the negative charges. So let's consider that we take a charge and we put it in this electric field. So let's say we have this positive charge, just plop it down in there, just like we're putting a mass in a gravitational field. And we're going to see what this electric field does to that charge. So we know that this charge feels the electric field, and we know positive charges will try to follow the electric field lines. So there's a force that goes down in this picture along the electric field, like that. And it will cause it to move through some distance down to some later point. Let's call this distance d. Okay, so d is the distance traveled along or parallel to the electric field lines. So we know that the electric force is Q times E. And we know that, again, if we apply work to this, the work done by the electric field is the force, which is QE, times the distance D. And if we want the potential energy from this, all we have to say is that, going back to energy concepts, the change in potential energy is equal to the negative of the work done by some conservative force, which in the electric force is a conservative force, so we can apply this concept. If that's the case, then we conclude that the change in potential energy of the object is negative Q ED. So this is the change in electric potential energy by moving some distance along the field lines. Now this distance, which has to be the distance along the field lines, so D is defined as the distance parallel to the electric field E. This has to be the case because that's the only way we're going to change our potential energy. So if we go back to the gravity example, if we know a little bit better how gravity works, the higher you lift the object up, the more potential energy it has. So by taking the object and moving it up higher, when I drop it, it would basically say that there's more work that can be done by gravity to move it to its final destination. So the higher you move it up against the field, the more potential energy it has. If we were to treat this example like gravity, it would also say that the higher we move this charge up in this electric field, so the further we move this charge against the electric field lines, when we let it go, it's going to have more distance that it could possibly cover to move from one place to another. So it has more potential energy. It has more ability for work to be done on it by the electric field. So if you notice though, if I were to take, let's say, the mass in a gravitational field, if you didn't move it up or down to change its height, let's say if we move it side to side parallel to the ground, it wouldn't change its potential energy because it's the same height off the ground in either situation. So there is no change in potential energy if you slide it perpendicular to the gravitational field. So the same is true in an electric field. If you remove this charge perpendicular to the electric field lines, it would not change its potential energy. So this distance has to be the distance that's parallel to those electric field lines. So we have this positive charge will decrease its potential energy as it moves along with the electric field. It will increase its potential energy as it's moved against the electric field, and there will be no change in potential energy when you move it side to side. Now, if you were to do this with a negative charge, the opposite would be true. Because unlike gravity and masses, where masses will attract to other masses and it goes one way pretty much, then if you take this negative charge and you release it from some point, it's not going to go down with the electric field. It's going to go naturally against the electric field. So this charge would feel some electric force upwards in this diagram, and it would cause it to move along a path for some distance that goes up to somewhere up there. So what we're trying to say here is that for the negative charges, if you look at the direction that it naturally wants to go, which is the direction it loses potential energy in, it naturally wants to go against the electric field. So it will actually lose potential energy in the opposite direction as a positive charge. So then if you were to move the electron or a negative charge with the electric field, it would instead gain potential energy. But if you still move it side to side, it remains unchanged. So now we have the idea of potential energy, which involves having a charge in the presence of other charges and it interacts with those charges, so it gives you potential energy. Now, we want to define a new quantity which doesn't depend on that charge being present. So, for instance, recall that from electric fields, so with the electric fields, we would have some source charge, and it would be the source of some electric field that it would create. And we remember that this electric field does not depend on the presence of any other charges. This electric field is purely from the source being there. It's a very helpful quantity to talk about when you're just talking about sources. Okay? So we want to do something very, very similar with potential energy. So what we're going to do is we're going to define another quantity. This is called the electric potential difference. Okay. Often we just call it the potential difference. Also, a name that we call this is the voltage. Okay. So this is a quantity which only depends on the source being present. It doesn't depend on any other charges being present. So it's a very helpful quantity to talk about without other things to worry about. So what we'll have is that, we have a region of positive charge and some region of negative charge, let's say. So this is essentially our source. Okay. So we have a source of an electric field, and that we know that electric field will point positive to negative like this. Okay, so here we go. We have a source of an electric field, and there's our electric field. We know that there is going to be a potential energy involved if we put charges in this electric field and they do something. But let's say we don't do that. There should still be a way to talk about what would happen to them if we put it in there. Just like an electric field is a way of saying, this is what would happen to a charge, this is the force it would exert if it were there. So voltage, or potential difference, is defined as, similarly to electric fields, change in potential energy divided by the test charge that we put in it. So if we were to put some charge, lowercase q, in it, we would divide this out of that potential energy and we would get our potential difference or voltage. So notice the similarity between this and the equation for electric field, which is force divided by charge. So it has similarities to each other. Now, before anything else, the units of this. So the units we have on top is a potential energy. Energy is in joules. Charge is in coulombs. And we use this quantity often enough that we don't continue to write joules per coulomb all the time. We often resort to calling it a volt. So we abbreviate V for volt. Okay? Now, before we continue on, I'm going to define an idea here to make sense out of the change in potential energy. So if we were to talk about process being natural or not natural, so do we have to force it to happen, or does it naturally occur on its own? So this is the idea of something being spontaneous. So spontaneous implies happens naturally, on its own. You don't need to do any work onto something to make it happen. It will just unfold. Okay, so then non-spontaneous would then mean the opposite, so then you would have to put work into it to make it do something. So the idea would be that if you were to like have, this hill, like that, and you have an object that is in either one of two positions, let's say at the bottom of the hill and then also at the top of the hill. And, you were to, let's say, take the one at the top of the hill, call this point B. If you were to have it go down the hill, you wouldn't need to force it to do that. It would happen on its own. So this object would go down the hill spontaneously, and we know from that it would lose potential energy. So this is spontaneous, and we know we lose potential energy, which is the same thing as saying that delta U is a negative value. The change in potential energy is negative, so final minus initial gives you a negative value. You end up with less potential energy than what you started with, so that's what we say. Down here, if you were to move this one up the hill from point A towards point B, it wouldn't roll up the hill on its own. You would have to force it to go up the hill against gravity. So we would say that this is non-spontaneous, and hence we have to increase its potential energy, so the value of delta U is positive if it's non-spontaneous. So we want to keep this in mind when we're talking about the potential energy, whether if it's gravity or electricity. So let's say we go back to this idea of, here's the electric potential difference or the voltage that we've defined. It depends on that change in electric potential energy. So it does depend on whether if it increases or decreases the potential energy. So in other words, one of these two scenarios. But we divide out the charge. So let's say if we took a look at the signs of this. So let's say if we consider a scenario, let's use this picture as our example. Let's say for positive charges, okay, so again, we don't need to have that there be a charge in this electric field for there to be this quantity, the potential difference or voltage. We're claiming that this quantity will exist in this picture regardless of whether we put something in it or not. Okay? But for the sake of understanding, if we were to put a charge in it, let's say this positive charge, okay, and let's say you were to just let it go, okay, so we let it do whatever it wants. We know that this positive charge would naturally or spontaneously move downwards to a new position. So during this process, we know that the change in potential energy is negative. So if we write delta V, we would plug in a negative number for our change in potential energy. And since it's a positive test charge, we would plug in positive into the bottom for Q. So the value for delta V that we get is negative. In other words, if we were to talk about the potential energy will start out with a higher number and it will decrease potential energy. But this also says that if we start out here, we will start out with more potential and we will decrease our potential as we drop down. So it follows with the change in potential energy. So from this, we can already say, okay, if you're higher up in this diagram or if you're further upstream of the electric field, you go more against the electric field, this region of positive charge, we're going to say is going to have a high value of V, a higher value of V for our potential. Which would then mean that down here, we have a lower value of V, so low V. Okay. If this holds true, we should be able to also do this for a negative charge and still have that this stays in place. So if we were to do a negative charge, so we put a negative charge in that electric field, let's say we let it do what it wants, so it will naturally move in the direction against the electric field toward the positive charge. And so we say, okay, for the negative charge, delta V equals, so we are decreasing its potential energy because it happens on its own or naturally. It will move towards the positive charge on its own, so it's decreasing potential energy upwards instead of downwards. But now it's a negative charge, so minus minus makes it a plus. So what this says is when that negative charge does move spontaneously on its own, it will move in a direction that increases its potential. So it will go from low potential to high potential, which is what we already said for the positive charge, just in the opposite direction. So regardless of what the charge is or what it's doing, it doesn't matter. Positive charges, positive source charges, are associated with higher potentials, and our negative charges are associated with lower potentials. Okay. So the potential, and hence the potential difference or change in potential as you go from one potential to another, that is set in stone. It does not change regardless of what you do in this picture. If you have positive charges and you have negative charges, and hence there's an electric field, you can say where the higher potential is and where the lower potential is, period. Okay. So this is a very powerful tool. Now, one last thing that we'll take a look at. So we have this definition for the change in potential. So if we were to plug in the equation for our change in potential energy, which we said was negative QEd, where d is the distance along the electric field lines, and we divide out the charge completely disappears. So there's no dependence on that charge being there. So delta V is negative E times D. So if we know the electric field and the distance involved, we can calculate what that change in potential is in volts.